So this will sort of be our last detail in 3.2 and 3.3. And some of you might have figured this out on your own, but if you didn't, I just wanted to make sure everyone was cool with this. And this is 0 as a 0. So every now and then you will be given a polynomial that might look a little bit different than some of the other polynomials because you're not going to see a constant term in it, for instance. So you might get a polynomial that looks something like f of x equals x to the 4th plus 7x cubed, and we'll say plus 12x squared. Now what you'll notice about this polynomial is it doesn't have the x term at the end, and it doesn't have the constant term at the end like many of our polynomials do. And in fact what it has is it has a common factor that's not just x, but x squared. So what you can do with this, instead of doing any synthetic division or anything that's complicated like that, you actually factor out an x squared, like this. And that leaves you with x squared plus 7x plus 12. Then, suddenly we're down to x squared in a quadratic. We factor that quadratic, x plus 3, x plus 4, and there was really no synthetic division to do. What's important to realize about this particular polynomial is that one of its zeros, Z-E-R-O, is the number 0. Because of there being an x in every term, if you plug the number 0 into this equation, you will get a result of 0. So you could think of this in front, even though people don't usually write this. You can think of this first thing right here as this. And you're not ever going to see anyone write that. That's not something people do, is write x squared as x minus 0 quantity squared. But it does help us see that the number 0 is one of our zeros. So if someone told me to give all the zeros of this one, I would say they are 0, -3, and -4. And I might even make a little note that this particular 0 has a multiplicity of 2, meaning it was an x squared, not just an x, so it kind of showed up twice. And if we get so used to doing synthetic division and so used to using quadratic formula, completing the square, and all these other fancy techniques, we sometimes forget one of the most important techniques for working with an equation, and that is you can factor out a greatest common factor. And in this case, we can pull out an x squared, and we can see that, yes, indeed, the number 0 is one of our zeros. Everyone okay with that? And that can mess you up if you're not ready for that to happen. I mean, I have confidence in all of you that you can do this now, but as I said, if you're just not ready for that, because we hadn't done one like that before, and now we've seen one. All right, and that's pretty much going to wrap up section 3.2 and 3.3. And we're going to move on to section 3.4, of course. And the big idea in section 3.4 is graphing these polynomials. Being given a polynomial equation and generating the graph. And I think it's actually kind of fun to graph these, and hopefully you will too once we get to that point. But as most things in this class, we have a lot of build up to get to where we actually need to be at the end. We have a lot of tools we need to build, a lot of things we need to establish for ourselves. So the secret to graphing is graphing a polynomial is based on a few ideas. Graphing a polynomial. We need the degree of the polynomial, which we were talking about at the very end of class last time, and we'll talk about more today. Need the degree. We need the leading coefficient, which I mentioned very briefly last class, and we'll work more on that today, so we'll figure out what I mean by that. If you don't remember me dropping that term last time, I'll use it again today. We need the zeros, and more importantly than the zeros, we need the real zeros, because the real zeros give us our x-intercepts. We'll need those. And we need the multiplicities of the zeros. In other words, if a factor is repeated and a 0 kind of shows up twice, much like x did, or 0 did in that previous problem, we need to know that too. So in order to graph a polynomial, we'll need the degree. Fortunately, the degree is not hard to find once you know how to find it. We'll need the leading coefficient. Fortunately, that's not hard to find once you know it. And we need the zeros. And that's pretty much what we've been working on for the past few days of class, is finding zeros. So we have a lot of skill in that area. So this is really just taking one more step. There's some good news for us, and that is, in section 3.4, our polynomials are usually, not always, usually given in factored form. And if a polynomial is given to you factored, is it pretty easy to spot the zeros just by looking at it? That's great news for us. That's usually the hardest thing to find, is the zeros. And if it's given to us in factored form, they've kind of done most of the work already. Some things we need to remember, one big thing we need to remember actually, is all polynomials have domain negative infinity to infinity. And what that really means for us today is the graphs will go left and right forever. When we draw a graph of a polynomial, we need to make sure we use arrows to show it is going off to the left and the right forever and ever and ever. All polynomials, or all polynomial graphs, I will say, other than the lines, we don't need to worry about graphing the lines today because we already know how to do that. So all polynomial graphs except for straight lines are smooth, continuous curves. Every graph that we draw today is going to be a smooth, continuous curve. By smooth, I mean no sharp corners or kinks. I'll show you what I mean by that in a moment here. By continuous, I mean no holes or gaps. What we used to say for that was when you draw it, you never have to lift your pencil up. You can do it all in one go. Curves is just our word in mathematics to mean not lines. Anything that's not a straight line we usually call a curve, meaning it curves, it bends. So, class, if we can analyze a polynomial and figure out some information about it, we can actually draw a pretty good sketch of the graph. And when I say draw a sketch, here's what I mean. We are going to draw neat sketches. And a sketch means they will be neat and accurate, but not show every detail. And I'm going to tell you right now, I'm not going to keep a secret from you, I'm going to tell you why our graphs are not going to show every single detail. It's because some of the polynomials that we graph today, and I'll write down a short version of this in a second, some of the polynomials that we graph today have very high y values on them and very low y values, like y values that are up like 100. So we're not going to do so much scaling on the y-axis. All right, so we know where we're headed. We're going to draw polynomial graphs, and I told you we need some information about them, and then we're going to draw these nice, smooth, continuous curves. So let's look at an example of what some polynomial graphs might look like. I actually did this ahead of time. I just drew a picture and then copied it for today. So polynomials and not polynomials. Copy. So these are some pictures drawn by me. Of course, you can tell that because you know what my writing looks like. And there, in those 4 blue pictures you see right there, that's what I mean by smooth continuous curves, everyone. There's no sharp corners on them. They go forever, left and right. Some hit the x-axis, some don't hit the x-axis, but nice, smooth, continuous curves. Things that are not polynomials are going to look maybe something like this. Absolute value has a sharp corner. It's not a polynomial. This one has sort of a kink in it, like a hard corner in this one. So this one's not a polynomial. This third one is not a polynomial because it's not continuous. In fact, it looks like a piecewise function to me. It's not continuous. There's a gap in it. And the last one's not a polynomial because even though it's a nice, smooth, continuous curve, it's not a function. So we're not going to be drawing anything that looks like any of these red ones on the bottom. We're going to be drawing things that look like these blue ones up here. And believe it or not, before today is done, I'm going to have you drawing pictures like these. It's going to be kind of cool. All right. So now we kind of know what a polynomial graph should look like. We're going to talk a little bit now about what we were talking about at the very end of class last time. Here is a picture, or I'm sorry, not a picture. Here is an equation for an unfactored polynomial. And 2 things you can pull off of an equation of a polynomial very, very quickly are the degree, which is the highest power you'll see, and the leading coefficient. Leading coefficient is with x to the highest power. So the degree of this polynomial is just going to be 3. That's the highest power I see there, so the degree is 3. Done. The leading coefficient is the coefficient that's with the x that has the highest power on it. So the leading coefficient of this one is 7, because there's a 7 in front of the x cubed. It turns out what's going to be interesting to us later, everyone, so I'll give you a little heads up about that right now. The question we're going to be asking ourselves is this. Is the degree even or odd? And is the leading coefficient positive or negative? Those are the questions we need to ask ourselves after we identify the degree and the leading coefficient. Now, I'll tell you why we need to ask those questions later. But for right now, just keep it in your minds that after we identify a degree and after we identify a leading coefficient, we're going to ask these 2 questions about our degree and leading coefficient. So here's the thing that is going to mess us up a little bit. We love factored polynomials because factoring is the hardest part. So if it is factored already, most of the work is done. But, ... when we are given a factored polynomial, maybe with some factors that have high multiplicities on them, it changes the way we identify the leading coefficient and the degree especially. Because what we need to imagine, everyone, when we're looking for the degree, is what would happen if someone were to multiply this whole thing out. If someone were to multiply this whole thing out, what do you think the highest power you would see on an x is? It would be 6. Because if someone were to multiply this out, we'd have 1x from this x minus 3, 2x's from this x plus 5, and 3x's from this x minus 7 because of the powers on those. So what I told you before about the degree being the highest power is true, but that rule only really works when you're looking at it in its unfactored form. So when we have something like this, if all factors are x plus a number or x minus a number, or x, you add powers on factors, including invisible ones, to get degree. And what do I mean by invisible ones? I mean that we know that even though I didn't write it, there's a 1 on this one right here, on the x minus 3. So, that being said, and I already asked this, and it was already answered, but let me ask again, what's the degree of this polynomial? 6. And the way that was found was by doing 1 plus 2 plus 3, by adding the powers that we saw. The leading coefficient should be in front of the first factor, and it could just be 1 or -1. So don't be alarmed if you don't see a number in front of the first factor. I don't see a number written here. If there's no number written there, what number do we assume is there? 1. So therefore, our leading coefficient for this one is 1. Because even though it wasn't there visibly, there is a 1 right there. So how does this mess people up? The big way I see this messing people up is they forget, is this a situation where I'm supposed to add them, or is this a situation where I'm supposed to look at the highest one? So just try to remember, and I know math can be dangerous to fiddle with, but just remember, if it's unfactored, degree should be the highest power. If it's factored, degree is add the powers on the factors. And like anything else in math, this will take us some practice to do, but we can do it. We'll be all right. As long as we know that's something we have to look for. Okay, so what's the drill going to be today? What's going to happen when we finally get to where we're going? I will show you. We're going to be presented with polynomials like this. The mistake degree that someone might write for this is they might say it's 4 because they looked for the highest power. Or they might say it's 4 plus 2 or 6 because they added the 2 and the 4. But what is actually the correct degree for this one? 7 because it's 2 plus 4 plus the invisible 1. So the correct degree for this one is going to be 7 because it's 2 plus 4 plus 1. The leading coefficient is not very exciting on this one, but we're still going to write it down. I don't see anything in front of those first set of parentheses, so what's my leading coefficient, everyone? Just 1. Later on today, what's going to be interesting to us is that the degree is odd and the leading coefficient is positive. That's going to be interesting to us in a little while. Then we jot down what our factors are. And our factors are x plus 5, x minus 3, and x plus 1. Can we turn factors into zeros pretty easily? The 0 is just the number that makes the factor equal to 0. So this is where you switch the sign. So if it's x plus 5, what's the 0? Negative 5. So it'll be negative 5, positive 3, negative 1. Can you hear okay in the back corner there with the door open? If it gets too bad, you can close it, of course. Our x-intercepts, are these zeros all real numbers? Yeah, so we can turn them all into x-intercepts. Negative 5, 0, 3, 0, negative 1, 0. And the last thing we're going to do now is we're going to write down the multiplicity. And the multiplicity is just going to be the power on the factor. So what was the power on x plus 5? You have a 2 on x plus 5. Yeah, you got to look back into the equation, sorry. What is the power on x minus 3? 4. 4? What is the power on x plus 1? 1. And of course, if you add these all up, you should get 7, which is, once again, your degree. That right there, it turns out, once I give you one more little trick, is going to be enough to draw a really good picture of a polynomial. And we'll get to our little trick soon, but we got a little bit more work to do before we get there. But, does anyone have any questions about how we analyze one of these things that's factored? Either by finding the degree, the leading coefficient, the factor, zeros, x-intercepts, or their multiplicity. Does anyone see mysteries or secrets out there? Okay. So, let's summarize a bit. I know we already said some of this stuff, but let's summarize a little bit here. Leading coefficient. If it's not factored, it is the number in front of x with the highest power. Just the number, not x, just the number. So when you write down your leading coefficient, you don't write 7x squared, you write 7, not 7x squared. It's the number in front of the x with the highest power, and if it's factored, you do need to make sure that all factors are x plus c, x minus c, or x, and it will be the number in front of parentheses. Just the number, even if there is also an x. I'll show you what I mean by that later. But the leading coefficient is always just the number. You should never have an x with your leading coefficient. And when I say just the number, even if there's also an x, you'll see what that means in a little bit. All right, leading coefficient. So, class, don't let people that write dumb-looking equations get in your way. The degree, this is not factored.
9.
So what's the degree?
9.
11. Highest power, right? Highest power is 11, so the degree is 11. What do you think the leading coefficient is?
Negative?
It is negative 8. Absolutely, you do need the negative sign, so don't forget the negative. What's interesting to me about these two things? What's interesting to me is that the degree is odd, and that the leading coefficient is negative. There'll be a reason for that later. Now, let's say someone gives you this one. And they ask for the degree and the leading coefficient. What's the degree of this one?
29.
Say again?
29.
8. 5 plus 2 plus 1. Degree is 8. 5 plus 2 plus 1. What's the leading coefficient? What number is in front of you though you can't see the number itself? -1. Very good. I'm sorry people were saying it and I didn't hear you. -1. What's interesting to me about this is that the degree is even and the leading coefficient is negative. Here's a trickier one. Here's a trickier one for everyone. All right, everyone. Now, it turns out, before I even ask you for the degree, I want to remind you that even though we don't usually write this, you can think of that x to the 4th right there as x minus 0 to the 4th. People won't write it like that, but I do want you to remember you can think of it like that. So that being said, what's the degree of this one? 10. 4 plus 5 plus 1. We cool? Degree is 10. Oh, that's interesting. The degree is even. Where did it come from? 4 plus 5 plus 1. The leading coefficient for this one? This is what I said before. You look at what's in front of all the parentheses, and even if there's an x there, you still just take the number. So what's the number that's in front of all the parentheses? 12. Not 12x to the 4th. You don't bring the x with you, just the number in front. It's okay to be getting these wrong right now, everyone, because we're learning these right now. But I would like you to ask questions if you don't see how we did the answer to any of these 3 problems here. So did anyone... It's okay if you got it wrong when I first asked, but is anyone still confused after you hear the correct answer? Any problems? So here's what we'll say. The degree is the number of factors, always. Remember that some could repeat and x counts as a factor. X squared is 2 factors, and so on. So absolutely, the degree should be the same as your number of factors. We just have to remember that every now and then factors repeat, and just an x by itself, that is also a factor. And x squared is 2 factors. X cubed is 3 factors. So the degree is the number of factors every time. If all factors are unique and all zeros are real, then the degree is the number of x-intercepts. If every factor is different from every other factor, another way of saying that is they all have multiplicity of 1. All factors have multiplicity 1. And they are all real zeros, no imaginary numbers anywhere, then yes, the degree will be the same as the number of x-intercepts. But as soon as you start repeating factors by having high multiplicity, and as soon as you start putting in imaginary zeros, which we actually won't see too much of today, then you start losing x-intercepts as compared to your degree. But every now and then, you will have the same number of factors, you have the same number of x-intercepts as your degree, and that's because all of your factors are different, and all of them are real zeros. For instance, Oops. Notch that one up. This is a 5th degree polynomial whose graph has 5 x-intercepts. Because none of the factors repeat, and they're all real numbers. This is a 7th degree polynomial whose graph has 2 x-intercepts due to repeated factors and imaginary zeros. Even though this one is a 7th degree, it only has 2 x-intercepts, -2 and 1. Why? Because these 2 factors are imaginary, no x-intercepts, and these 2 repeat, which eats up some of our x-intercepts. All right. If your unfactored polynomial has an x in every term, in other words, there's no constant term, then 0, 0 is one of your x-intercepts. If you're looking at an unfactored polynomial and every single term has an x in it, then 0, 0 is one of your x-intercepts. Because if every term has an x in it, the first thing you can do is factor out an x. And then, since x is a factor, 0 is a 0, and 0, 0 is an x-intercept. So just be aware of that every now and then you're going to have a graph that hits right at the origin, 0, 0. The graph's going to hit right at the origin. And how do you know that's going to happen? Because every term has an x in it. Similar to that, if your polynomial is factored and in front of the parentheses you have x or x to a power, then 0, 0 is an x-intercept. In other words, if you have a factored polynomial, and I don't really care if there's a leading coefficient out in front now, I don't really care what that is, but what I'm trying to tell you is that if there are some x's hanging out in front here, or x to a power, it means the same thing. It means that an x got factored out, or in this case 3 x's got factored out, and 0, 0 is an x-intercept. And you can see that, everyone, because look at this. In fact, let me add something up here, too. Does everyone agree that with this one up here, if you put a 0 in there, it's going to kill off every single term? Yes. Yeah. And with this one down here, if you put a 0 in here, what's going to happen is These two things are going to do their own thing, this one and this one, but you're still going to multiply the whole thing by 0 right here. And if you're multiplying the whole thing by 0, we can basically say 0 times stuff is still 0. So that's why that works. The power on x is counted like any other multiplicity. All right. All polynomial graphs have end behavior. And there are 4 types to choose from. End behavior refers to what the graph eventually does as you go far enough left or far enough right. End behavior. What the graph does if you go far enough left out towards negative infinity or right out towards infinity. Actually, everyone, this is a good opportunity to tell you this. If you ever see an arrow like this in math, the way you read that arrow out loud is the word approaching. So if someone writes arrow negative infinity, they mean we are approaching negative infinity. In other words, we are going way out far out to the left on the x-axis. Okay, so we're talking about what does the graph do as you go way far out to the left or way far out to the right? Well, I prepared another picture for you. Let me show it to you. End behavior right there. Copy. Huh. I appear to have frozen my whoa. Here are 4 polynomial graphs, nice, smooth, continuous curves. And what I'm showing you here is the different things that these graphs can do. Now, this is not to be confused with the ideas of increasing and decreasing, where we always move left to right. When I use these terms, falls or rises, left or right, I'm simply talking about which direction the arrow is pointing. Is the arrow tending upwards or downwards? So some polynomial graphs, the arrow is going to go down on the left and up on the right. Some it's going to go up on both sides, some it's going to go down on both sides, and then you can also have it rise left and fall on the right. Eventually, after a polynomial does all its nice smooth wiggling and hits all of its x-intercepts that it might want to hit, it's eventually going to make a choice. And as you go off in either direction, you're either going to go up forever or down forever. There are 4 possible options, and here they are. And it turns out, class, to determine the end behavior of any polynomial, you ask 2 questions. And the 2 questions are this. Is the degree even or odd? Is the leading coefficient positive or negative? Let me show you a really quick example of this. With a very simple polynomial. That's a pretty simple polynomial, but it's not that hard to analyze it using our new techniques. First of all, what's the highest power you see? This is not a trick question. 2. The degree is 2. And what's the leading coefficient? 1. What's interesting about those two things is that the degree is even and the leading coefficient is positive. And it turns out that if your degree is even and your leading coefficient is positive, that tells you that you have this type of end behavior, everyone, that you go rise on both sides. And is that exactly what our original parabola did? Did it go up on both sides? Yeah. Look at this one right here. X cubed, you remember this guy? Looked kind of like this. Well, it turns out the degree of this one is 3. The leading coefficient is 1. The degree is odd. The leading coefficient is positive. And it turns out the rule is if you have that type of end behavior, if you have that type of situation, then your end behavior looks like this. So what are the rules? Well, I made you a picture. I think I'll save it before I bring up that picture. Oops. This right here tells you how to determine the end behavior of your polynomial. Just by deciding if the leading coefficient is positive or negative, and deciding if the degree is even or odd. This doesn't tell you about all the x-intercepts. It does not tell you everything the polynomial does. It just tells you that eventually, as you move out far enough to the left or far enough to the right, what the graph is going to do. So, if someone gave me a polynomial like this, f of x equals negative 3x to the 4th plus 8x squared minus 12x plus 11, I don't know off the top of my head what the x-intercepts are because this is not factored. Nor do I feel like factoring this right now. But because it's unfactored, I can very easily identify both the degree and the leading coefficient. I can tell everyone that the degree is 4, which is even, and that the leading coefficient is negative 3, which is negative. So I go over to my chart here, and I find even, negative, this guy right here, which means the graph, however it looks, will eventually go down on both sides, or fall on both sides, however you want to say it. It will turn out, everyone, that if you put just a little bit of time in it, it's actually not that hard to remember this chart. And the main way I remember this chart is I remember these two graphs, x squared and x cubed, the even and the odd degrees. And then I remember that the leading coefficient's negative, it's just flipped from that. So I use x cubed and x squared to remember that chart. All right, still building up, we're almost there. I do see the time, we will take a break soon. Just want to build up a little bit more. Once you know your x-intercepts, which is easy if the polynomial is factored. I mean relatively easy, everyone. I don't want to say anything's easy in this class. But if the polynomial is factored, it is easier to find your x-intercepts. Once you know your x-intercepts, you use multiplicity to determine how your graph touches the x-axis. So some people might say, Steve, what do you mean how the graph touches the x-axis? Well, let me show you another picture. This one is called, there we go. Oops. I did this graph, this enormous graph, using a computer program called Desmos. It's free to everyone on the internet. It's like this online graphing calculator. It's pretty awesome. If you want to look it up, it's a pretty cool site. Oh, here's what I wanted to show you. Here is a picture of a polynomial, and it's got 3 different x-intercepts. And I want you to take a moment and I want you to look at those x-intercepts, and I want you to realize that they are all quite different from each other. At the first x-intercept, over here, we like to do what I call a bounce. You've seen that before, the way the x squared parabola bounces off the vertex at the origin. This one right here, we call a cross. You just go right across the x-axis, no hesitation. Which is slightly different than this one, where it looks like you're going to bounce, but you don't. I call this a cross and flatten, but I will also accept the term wiggle. It makes a difference. And it turns out what determines the way you cross or bounce off the x-axis, your behavior at the x-intercept, is based on the multiplicity. So, class, let me show you this. X-intercept behavior, copy. Here's a picture showing all the different, for crying out loud, we're going to get seasick watching this video. All right, here's a picture showing all the different behaviors: the cross, the bounce, and the cross and flat, or the wiggle, whichever you want to call it. I really don't care. This is what happens if your 0 has multiplicity 1. If your multiplicity is 1, you're just going to cross right over the x-axis. No wiggling, no bouncing, no hesitation. You just shoot right across like you would with a line. If your multiplicity is any even number, 2, 4, 6, 8, if the multiplicity on the factor or the 0 is any even number, you bounce off the axis. You do not cross over it, you hit it, you turn right around. Not like the absolute value function. It's not a sharp corner, it's a nice, smooth bounce. That leaves this one over here. That means 0 has any odd multiplicity bigger than 1. This one's hardest for people to remember, but this would be if like your multiplicity was like 3, 5, 7, or 9. In other words, an odd multiplicity you always cross.
Any
odd multiplicity bigger than 1.
Yeah, any odd bigger than 1. Okay.
Yeah, any odd bigger than 1. So you're still going to cross on any odd multiplicity, but when it's bigger than 1, when it's like 3, 5, 7, or 9, you do this little wiggle action. Have we ever seen this wiggle action before in a graph? Did we see that on x cubed? It's just like x cubed. So another way of thinking about it is this is similar to y equals x. This is similar to y equals x squared. And this is similar to y equals x cubed. 1, 2, 3. So when you're drawing your graph and you're drawing your x-intercepts, not only do you need to make sure you hit the x-axis in the right place, you need to make sure that you are doing the right behavior. Okay, I think that's enough. We will take a break. So usually in Math 121, a bounce is just a bounce, and a cross and flatten is just a cross and flatten. So once you get that bounce down, you're in good shape. Once you get that cross and flatten down, you're in good shape. But it turns out as multiplicity gets higher and higher, we do see more flattening with both the even and odd multiplicity. And this is very hard to show by hand, but I did do some more pictures using Desmos to show you what I mean by that. Here what I did was I asked the computer to go ahead and graph x squared, x to the 4th, x to the 20th, and x to the 100th. Now what actually happens here, everyone, is in all of these, 0, 0 is an x-intercept, but with different multiplicities. Now this one here is called the parabola, because it comes from a quadratic. The rest of these are not parabolas. All three of these are not parabolas. But what you can see is as the multiplicity gets higher and higher and higher, the bottom gets flatter and flatter and flatter, flattens out like a flat tire, almost to the point where this last one doesn't look like a function. Does everyone see that? It almost looks like it's a pair of vertical lines and a little horizontal line, when really what it is it's just very, very steep. But it's still a function, just a very, very steep function. So this is what I mean when I say as multiplicity increases, you see more and more flattening. But we don't need to worry about that. I'm not going to be going in there and saying, well, this looks more like an x to the 5th, not an x to the 3rd, or something like that. Or this looks more like an x to the 6th, not an x to the 8th. But I do want you to understand that we do get more flattening as multiplicity increases. And this also happens with the odd ones as well. These are a little bit bigger looking. But what I have here is I have x cubed, x to the 5th, x to the 19th, and x to the 101. And once again, these all have 0, 0 as their x-intercept. But with different multiplicities. So what's happening? The higher the multiplicity, the more flattening you see, until it almost just looks like a pair of straight lines. But it is still curving there. It's still doing a wiggle or a cross and flat, whatever you want to call it. But it just gets more and more severe as your multiplicity goes up. So just be aware of that, everyone. Just be aware of that difference. If you're ever doing this like on a computer, you're like, why does this look different? It's because it does make a difference. The basic behavior doesn't change, but the appearance does change slightly. We get more flattening. And now it's time for us to put all of our ideas together. So, join me if you will, as we analyze a polynomial. I think you'll like this, it's pretty cool. First example always takes the longest, but it will be pretty neat. Here we have a polynomial, everyone, and it's nicely all factored for us. And the reason we love the factored polynomials is because it'll be much easier for us to spot what the zeros are when it's factored. The first thing I'll do is I'll jot down the degree of this polynomial. And because it's factored, I add up the powers, even that little mysterious one that I don't see there because it's an invisible 1. So what is the degree of this polynomial? 6. What's important to me about that number specifically? That's what kind of number? It's an even number. The leading coefficient is easy to spot if you know where to look for it. It's just in front of all the parentheses. What is it? Negative 3. What's important to me about that number is that it's negative. So, I could go back and look at my chart, but here's what I know, everyone. Here's what I know. This is why I don't always need to look at that chart. If it's even multiplicity, that tells me that it either goes up on both sides or down on both sides. If it's even multiplicity, it does one of those two things, much like a parabola would do. And because the leading coefficient is negative, it's not like our classic parabola, so it's got to be this one right here. And that's exactly what that little chart tells you, but you know, it's always better if we don't have to rely on a chart. So I know that this polynomial, after it does all its x-intercepts, is eventually going to go down on both sides. All right, now I'm going to make a list, and it's going to be factors. I guess I can put zeros in there too. We'll do zeros. We'll do all of this for the first time through. Zeros, x-intercepts, multiplicities, behavior. We might shorten this chart on our next problem, but for this first one, we'll do all the little details. The factors are x plus 4, x plus 1, and x minus 3. That means the zeros are negative 4, -1, and 3. That means the x-intercepts are -4, 0, -1, 0, and 3, 0. As I said, maybe you don't need this much detail when you're doing them later, but for our first example, we're going to put all the details in. The multiplicities, you look on the powers that appear on the factor. What's the multiplicity of x plus 4? 2. What's the multiplicity of x plus 1? 3. What's the multiplicity of x minus 3? 1. Safety check. Add these up. You should get your degree. You should get your degree right there. Behavior, what I was talking about before, there are 3 possible behaviors. You either cross, just like a line, you bounce, just like a parabola, or you wiggle, just like an x cubed function. So when the multiplicity was 2, kind of like a parabola, what do? We bounce. When the multiplicity was a high odd number, what do? Just like the x cubed function. We wiggle, or we cross and flatten. And when the multiplicity is just 1, what do? Straight up. Just cross it. Okay, that's all the information we need. Now the way we graph these things is a little bit different than the way we graph our traditional graphs that we do in this class. I don't do it with a full grid. I'm going to show you the special grid I made just for graphing these things. Let me bring it up here for you. The polynomial graphing grid. Cool. Copy. And if you want to make one of these, it's not that hard. You just want to make it really, really wide. Make a really wide grid. Give yourself plenty of spacing between the values on the x-axis, and actually don't even bother labeling the y-axis with numbers. So on this particular example, it should be enough to go out to maybe like 6 and -6 on your x-axis. That should be far enough. But don't try to make this small. If you're going to play along with me and draw a graph with me today, don't make it small. Give yourself plenty of room. And I'm going to show you how I do this. And maybe as you do this later, you'll come up with your own little tricks. You'll come up with things that will help you that I don't do, or you won't want to do something I do. But I'm going to show you what I do. First thing I do, once I get my big wide graph that's just numbered on the x-axis, not the y-axis, is I put 2 little arrows in to remind myself what my end behavior was going to be. I just said this one was going to fall on both sides. So I put those 2 little arrows there to remind myself that when I sketch my graph, I need to fall on both sides. Next thing I do is I go through and label my x-intercepts. In this case, I had 3 of them, at -4, -1, and 3. -4, -1, and 3. Nice and wide, so I have plenty of room to show my work. Then, so I don't have to keep looking back and forth between my work and my graph, I write myself a little hint about what I'm going to do with those. For instance, up here on this one, I'm going to bounce. This one I'm going to cross and flatten. And this one I'm going to cross. Not right next to them. I don't want to mess up my graph. Just want to be able to look up there and see what am I supposed to do when I get to that x-intercept. Whether I'm going to bounce off it, whether I'm going to cross and flatten, or if I'm just going to cross. And when you get that far, go ahead and put your pencil down and just watch, and then I'll give you a chance to do the graph yourself in a moment. Because the secret to this, everyone, is you have to plan ahead. Because if you're going to do a cross and flatten, or you're going to do a bounce, you can't do a sharp corner. So you have to plan ahead. So watch what I do, everyone, then I'll let you do part of it too. I start from down here because I fall on the left. So I'm going to start down below, and I'm going to come up here and watch what I do. I come up early so I can do my bounce. Everyone try that. Add that to your graph. Go ahead and pick your pencils up, add that to your graph. I come up early so I can do a nice bounce. I don't come straight up at it, otherwise I have to do a sharp corner. I sort of do it like I'm drawing a parabola, if that helps you. And then I'm already thinking about what I'm going to have to do when I get to the next one. What am I going to have to do when I get to the next x-intercept? That one's going to be a cross and flatten. So watch what I do now. Just watch this part again. I come down. It really doesn't matter how far because we're not scaling on the y-axis. and I come up early again, almost like I'm going to do a parabola again, or a parabola-like shape. Go ahead and add that to your graph. But this, everyone, is not a bounce. It's a cross and flatten. So what I do is I kind of do the opposite on the other side, where I do a slow takeoff, like that. So it's sort of like someone took a bounce and kind of wrenched it around 180 degrees. Keeping your graph nice and smooth, when you get to the next intercept, you're just going to come straight down on it, because it's just a cross. And you cross over, and you're done. What's important? Well, should be smooth and continuous. No sharp corners, no kinks, and it's very, very easy to accidentally put in a sharp corner when you're doing those x-intercepts. Should have the proper end behavior. In other words, this one goes down on both sides. That's what we said it would do. It should have the proper x-intercepts end behavior based on multiplicity, which we did. We did a bounce, we did a cross and flatten, and we did a cross. We don't scale on the y-axis, because this ordered pair right here, where we hit the y-axis, everyone, actually ends up being 0, 144. That's why we don't bother to number our y-axis. Yeah, question?
How do you know when you should stop the curve?
Like, how do I know how high to go or low to go? That's the point of not scaling on the y-axis. It's kind of up to you. So when I did this right here, if I had wanted to, I could have gone like that and come down like that, just so long as I get the right shape. Does that make sense? Yeah, it's a great question. And we actually don't have the machinery in this class to know exactly how high it goes in the middle there. So we just kind of draw a sketch that shows the rough shape of the graph. Very good question. Okay. Do we feel okay enough about that to work on a few more details? All right. This next part of the lecture is called What People Do Wrong. Where we'll just call it Making Mistakes. Actually, we'll call it Making Mistakes at your x-intercepts. It happens, everyone. It happens to everyone when they first start doing these, making mistakes at your x-intercepts. That's a bad bounce, everyone. It shows a sharp corner there. That's a bad bounce. Don't do that. That's also a bad bounce. Don't do that either. And just like an absolute value function is also a bad bounce. These are not parabolas, everyone, because they're not quadratics, but I want you to kind of think of a bounce that should look like the parabola did. Nice and smooth and curvy. Everyone okay with that? You gotta be careful when you do these. Okay. I don't know how many of these I'll do, but here's a bad cross and flatten, everyone. You come up and you're like, oh, I was supposed to flatten, so I'll just do all my flattening afterwards. No good. Oops. It's a bad way to spell bad. It's a bad wiggle. And this one I do see people do every now and then, so don't do this. It's amazing how easy it is to kind of freak out when you're drawing one of these for the first time and start making up stuff that you don't want to do. That's a bad wiggle too. Don't do that. And what you don't want to do is you don't want to hug your x-axis. Don't stay close to your x-axis. So if you've got like two x-intercepts like this, don't do this. I better stay down here because I got another one. Like that. That's no good. You want to make sure you get away from it and keep your graph nice and smooth and curvy. I'll call this a bad hug of x-axis. So it does take some practice to draw these graphs neatly, and like anything else in this class, you're not going to get graphing practice by doing the online homework. So there are more examples on YouTube for you to practice, kind of do along with me, and a worksheet with answer key, so you can practice some of your graphing by hand. Okay, let's do another example. All right. 2x squared, x minus 5 cubed, x minus 3, x plus 1, x plus 4 squared. What a long one this is. But I can handle this. I guess the first thing I should do is I should identify my degree. Plenty of ways to mess it up. You want to add up the powers, and don't forget the invisible 1. So don't write 3, even though that's the highest power. That's not what we're looking for right now. Don't write 7, because even though 2 plus 3 plus 2 is 7, that's not all of them. 9. Very good. Leading coefficient, is it 2x squared? Or is it just the number 2?
2.
Yeah, you don't bring the x with you. Even though there's x's there, you don't bring that with you. It's just 2. I like that the degree is odd. I like that the leading coefficient is positive. Now let me think for a second. Odd. Odd degree means up on one side, down on the other. And since it's positive, it's sort of like the x cubed graph. So this one, which you can verify with your little chart if you want, does do this. But it's also better to just kind of think your way through it. All right, now, here's the other thing that's very, very helpful to do. It helps to write your factors so the zeros are left to right. This will make your job so much easier when you graph it. If you write it so your factors are listed so your zeros are going left to right. It's not required, but it will help you. So if you look at this whole list of factors here, everyone, which one produces the 0 that is the most negative furthest to the left? X plus 4 does. So we write x plus 4, and then my x-intercept for that is going to be negative 4, 0. And that's just going to really help me when I draw my graph if I can just kind of look down my list as I go, and I'm going from left to right. What's the next one going to be? X plus 1. Now, everyone, be very, very careful with this next one. No one say anything out loud, please. Everyone just look at that up there and see if you can tell me as we move from left to right what our next x-intercept is. Don't say it yet. And this one, I'm making such a big deal about it because people forget this all the time. Do you see the one that people might be forgetting? What is it? It's 0. Because these are our factors, everyone. So it turns out that our next one is just x, because of this x squared in front. And that means the x-intercept that goes with it is 0, 0. Why did I just write x? Because I'm going to write the power later as the multiplicity. After that one, that people forget all the time, comes x minus 3 and x minus 5. So easy to forget that when it's 0. So easy. Which is why I make a big deal about it in class. Multiplicity, well, we can't see those at the moment. There they are. 2, 1, 2, 1, 3. I hear some chatter. Is there a question?
No, I was just wondering if the...
Once we write down our multiplicities, we do a little safety check. We add them up. 2 plus 1 plus 2 plus 1 plus 3, 9. That should be my degree. Means I didn't miss anything. And now I do my behavior. If your multiplicity is even, I don't care what even number it is, if your multiplicity is even, what do? You bounce. So we're going to have a bounce there, and we're going to have a bounce there. If your multiplicity is just the number 1, what do? You just cross over. If your multiplicity is some odd number bigger than 1, like 3 or 5 or 7, what do? You cross and flatten, or you wiggle, whatever you want to call it. This is going to be enough information to draw my graph, everyone. This will be enough information to draw my graph. I'm not saying it's going to be the easiest thing I've ever done, but it will be enough information. So I'm going to summon my graph, my nice wide coordinate system that has plenty of space on the x-axis, and I don't worry about scaling on the y-axis. Because even though, yes, it is interesting to know how high or how low this graph goes, it's not absolutely required for our sketch. All right. So my x-intercepts, I know you can't see them, but I have them written down. So rather than sliding back and forth, I'm just going to write them in. There's one here at -4. There's one here at -1. There's one here at 0. One here at 3. And there's one here at 5. What is this graph supposed to do? Eventually, it's going to be down on this side. And eventually, it's going to be up on this side. Personal choice, not something you are required to do, but I like to make little notes for myself about what I intend to do, oh Mary, what I intend to do at each one of my x-intercepts. I put them up here so they're not my way of drawing my graph, but just so I know what to do so I'm not always looking back and forth. Got to draw a smooth curve. Got to draw a smooth curve. Okay. Here I go. I'm going to try and do it all in one flow this time. Watch this. Bounce. Cross. Bounce. Cross. Cross and flatten. Now you're welcome to be thinking to yourself, I need to practice this. That's okay. But does anyone feel like I'm keeping secrets from you on how to do it? That's not my intention. My intention is to give you something that, yeah, you need to practice. Of course you do. Like most things in math, you can't just expect to be able to do this perfect your first try. I don't even do it perfect my first try. I sometimes have to erase and start again. And if you have to do that, that's fine. If you realize you were coming straight up at one of your x-intercepts and you were supposed to do a bounce instead, then erase it and try it again. I will tell you this, everyone, and I will remind you about this next week on the study guide. You will need to graph one of these on the exam. This is going to be an exam problem, not this one, but one of these, where I give you a factored polynomial. You've got to rip it apart into all its factors and x-intercepts. You got to do your end behavior, and you got to graph it. So what can go wrong? A couple little things. Let's talk about some of the little things that can go wrong. It's always something. At some point, you might be encountering the mostly factored polynomial. The mostly factored polynomial. And you can tell it's not completely factored because one of the factors doesn't look right. Which one of those factors doesn't look quite right? X squared minus 4. Someone has done most of the hard work for us, but they haven't done all of it for us. It is our job to realize that x squared minus 4 can be written as x plus 2, x minus 2. If you don't like that, look up this in the textbook. Difference of squares. That's what that's called, everyone. That's called difference of squares. It's a factoring technique. Once you factor that one, you put that in instead. But now we have a different problem.
We have 2 degrees.
We have what?
Degree.
We got the same factor twice.
Yeah.
So we got to group that together, otherwise we're going to mess up our multiplicities. And now it's good to go. There wasn't a whole lot of work we had to do, but we did have to do a little bit of work before we were ready to work with this one. Now we have all of our factors, like they're supposed to look, either x plus a number or x minus a number, and we have a squared rather than a repeated factor. So, well, it's still repeated, but now we can see its multiplicity and we know that we'll have a bounce there. So in order to use these techniques, you need factors that are x plus a number, or x minus a number, or just x. And write common factors with an exponent so you can determine multiplicity. All right. Now, let's say you are asked to graph this one. Why are you allowed to get very, very angry if someone tells you to graph this?
It's not in factor form.
It's not factored. It could have up to 7 x-intercepts. Does anyone feel like looking for 7 zeros right now? No, no one does. So, this will be a multiple choice graphing problem, not a straight up graphing problem. So, we analyze the few things we do know how to find. What can we find pretty easily just from looking at it as is? We can find the y-intercept quite easily, yes. The y-intercept would be 0, 5. Well done. We also know that it must have 7 or less x-intercepts. Does everyone agree that's a fair statement? I don't know if it has 7, but I do know that there's no way it has more than 7 because the degree is 7. What else can we do pretty easily?
Coefficient.
Leading coefficient, that's a good idea. And what do we often do when we're doing the leading coefficient? What's the other thing we find? Leading coefficient and the degree. Leading coefficient looks like -3. Degree looks like 7. Looks like we have negative leading coefficient. Degree is odd. That's going to be this guy right here. All right, now this is a multiple choice problem. So let's say that one of the choices looks like this. 1 x-intercept, 2, 3, 4, 5, 6 x-intercepts. Is that the right graph? Why not? Oh, this one has the wrong end behavior. So we can eliminate that one right off the bat. Wrong end behavior. No good. Okay, great. Wrong end behavior. All right. Is that the right graph? I'll tell you, I know that it's not.
The y-intercept.
Y-intercept is wrong. Wrong y-intercept. So you're telling me that I need that end behavior, but I need the y-intercept to be positive. So that must be the right graph.
It's a possibility. No.
Why not?
No, oh, it has more, yeah, intercept.
Too many x-intercepts? So if this was your multiple choice question, and these were 3 of the choices, they're gone. They're out of there, and you know it's the last one. You're not going to be able to figure out all the x-intercepts just by looking at an unfactored polynomial for the most part. But you can figure out these key pieces of information, and that's enough to eliminate some wrong answers. So when they give you a multiple choice question like this, they intend for you to eliminate impossible answers. And I know it's like an old study technique where you really know you're doing well in a multiple choice test if you pretend it's not a multiple choice and you figure out the answer on yourself and then see if your answer matches one of theirs. That's like a really powerful move when you're taking a multiple choice test, but that's not what they intend for you to do on this problem. They don't intend for you to figure out what that graph looks like. They intend for you to eliminate the wrong answers. So don't waste your time trying to factor that sucker, because I don't even know how that one factors. I just made it up. All right. Good. A few reminders for ourselves, everyone. End behavior of an even degree polynomial is always either up on both sides or down on both sides. This reinforces our idea that range can never be negative infinity to infinity, because this one only goes up forever, and this one only goes down forever. So one of the first things I told you about polynomials was that an even degree polynomial cannot have a range of negative infinity to infinity. And the reason is because of the end behavior. If it goes up on both sides, somewhere in the middle is the lowest point. If it goes down on both sides, somewhere in the middle is the highest point. I don't know where it is, but it's in there somewhere. End behavior of odd degree polynomial is either this or this. Up and down forever, so range is guaranteed to be negative infinity to infinity. Guaranteed. So is it possible at some point, we could encounter an even degree polynomial with no x-intercepts? Can that happen? Yeah, we already have. They're quadratic, some of those. But you could have an even degree polynomial that has so much jazz going on in the middle, but just never happens to hit that x-axis. All right. Let's do one more big idea today, and then maybe one more small one. You don't need to draw this picture with me, but you're going to use this picture in just a moment, because I am going to draw a picture for you. I'm going to put a point there, and put a point there, and put a point there. Everyone, your job is to give me the factored polynomial that creates this graph. And I will tell you there's more than one right answer. I want you to give me the factored polynomial that generates this graph right here. You can do this. Even if you don't know exactly what to do, go ahead and write down something. Write down what you know. Maybe you just write down the zeros. Maybe you just write down something about multiplicity or end behavior. You write down something. I'll tell you what I do first. so I'm not done, but am I off to a good start? Turning the zeros into factors, is that something a good place to begin? Yeah, but based on what you see happening at those zeros, based on the behavior, the multiplicity, we might need to put some powers in there. Does everyone agree with that? So just so we have it in our notes here, I'm going to write a 1 here. Even though you don't need to write a 1, I'm going to write a 1 there just to remind myself that we're doing a cross right there. But what are we doing at the next one? Bouncing. So what does your multiplicity or power need to be?
An even.
Even. So I'm going to write 2, but if you wrote 4, you're fine. If you wrote 6, you're fine. If you wrote 20, that's a little bit much. What are we going to do with the next one? That's a wiggle, so we need a 3. Now this is the correct answer, everyone, but if instead of writing 3, you wrote 5, you're okay. If instead of writing 2, you wrote 4, you're okay. The first one did have to be a 1. But here's what they're usually going to do, everyone, to avoid that problem. They're going to say this to you. They're going to say, give a factored polynomial of lowest degree possible. What that means, everyone, is that your powers will be 1, 2, or 3. They will tell you to do the lowest degree possible, and that's how they avoid you putting a power of 4 or a power of 5. Even though that would technically be allowed, they want us to keep it small. Is everyone okay with that? You want to try another one of these? Now that we all see the game? All right. I'm going to trick you on this one. And if you spot the trick, I want you to keep it to yourself so other people have an opportunity. So work on this one alone, please. Just because I don't want anyone giving up the game before I'm ready to give it up. Because I'm feeling especially sneaky today. But it does have an answer. The trick is, I'm not trying to trick you like, hey, this wasn't even a polynomial, what are you doing? I'm not doing that. It's not that much, so you should still try it. And I'll write the instructions in a moment, but what I want you to do is I want you to write a factored polynomial of lowest degree possible. And I'll tell you, class, this is one of my favorite trick questions. And if you spot it, if you're feeling especially clever, cover up your paper and keep it to yourself. I don't care what you call it. If you call it f of x, g of x, or h of x, it doesn't matter. Pay close attention to the questions I asked you. Did I get my zeros labeled correctly? My zeros look okay? -4, -1, 2, and 5? Okay, how do my factors look? Just the factors, don't worry about the powers at the moment. Just the factors look okay? Did I do them right? I did. I did, okay. How about my powers? Do they look okay? Lowest degree possible, so I can only use 1, 2, or 3. So I use 2 on a bounce, 1 on a cross, and 3 on a cross and flatten. Without saying what it is, does anyone know what's wrong with my answer? Raise your hand if you know what's wrong with my answer. What do you think is wrong with my answer? What do you mean by leading coefficient? I don't need a leading coefficient, do I? Oh, shoot. This one has end behavior that looks like this. This means odd degree and negative leading coefficient. What's the easiest way to fix that? Very tricky, very sneaky. Is that what other people with their hands up were going to say? Leading coefficient was off? That's what the problem was. Just because you have the right factors, just because you have the right multiplicities, doesn't guarantee you have the right equation. you might need to adjust your leading coefficient. So if you put a -2, a -3, a -5, a -20, a -7,000 there, that's fine. But you needed a negative number. So you did need this to be negative in order for this to have the proper end behavior that I show on the graph. It was a trick question. Well done. All right. Last idea, which I might just be able to scratch the surface of today, is going to be the intermediate value theorem. Don't let this spook you, everyone. All polynomials are continuous. No holes or gaps. They're nice, smooth, continuous curves. There's no break in them. All right. Here's what the intermediate value theorem tells us. Let's say that I was up here and I was graphing a polynomial. Nice smooth graph, everything's going well. When whoops, all of a sudden, part of my graph got erased. Part of my graph got erased. So there's some piece missing between this point and this point. This is still going to be a polynomial, everyone. I just erased part of it. And let's say the part of it I erased was between the x value of 3 and the x value of 7. Now, the intermediate value theorem is not the most glorious theorem you'll ever hear about. In fact, it irritates a lot of people because it doesn't really seem to tell you much at all. But here's the idea, everyone. I just want you to think about this very carefully. Does that missing piece have to cross the x-axis?
Yeah.
Absolutely. So what the intermediate value theorem tells us, well, actually, let me write the answer to that question first. Does missing piece cross x-axis? And the answer is a resounding yes. So here's what the intermediate value theorem tells us. If you are above the x-axis at one x value and below at another x value, then in between those x values, there is at least one x-intercept. What this tells us is because these graphs never break, because they have no holes, because they have no gaps, is it tells us that if you know you're above the x-axis somewhere and below somewhere else, then somewhere in there you have at least one x-intercept. And the reason I say at least is because we don't know if we have more than one. But we know there's at least one in there. And this is where we'll pick up next time, everyone. Thank you so much for coming. Have a great weekend. Do your homework.
Probably as well.
Thanks.